Section 7.5 starts off talking about how covalent bond energies can be used to calculate the approximate enthalpy of a reaction, a chemical transformation. We have to put energy into breaking bonds, but then when bonds get formed, we get energy back out. And the amount of energy per bond, we have a table of average bond energies. So the average bond energy that's involved in a carbon-carbon single bond, for example, or a carbon-hydrogen single bond, these average energies have been tabulated, and you can look at a reaction, see which bonds are being broken and which bonds are being formed, and follow this procedure to get an approximate enthalpy of the transformation. So this is not as accurate as the using the heat of formation of a specific compound, because carbon-carbon bond energies can vary depending on what type of molecule they are found in, and we're just using an average, like a typical value, rather than the specific value, so these are not quite as accurate, but the table can be a lot shorter because there's fewer types of bonds that you can make, rather than the enthalpy of formation, you need a specific one for each compound, and so that table can get pretty long and pretty extensive. So let's try doing a general approximation of the enthalpy of this reaction. Let's see what we have here. We have a hydrogen molecule, and we have a chlorine molecule, and we are making two hydrogen chloride molecules. I'll just draw a little stack over here. So these hydrogen-hydrogen bonds are being broken. So let's make a list of what's being broken. When we do this as written, 1 mole of hydrogen, 1 mole of chlorine, forming 2 moles of hydrogen chloride, we are breaking 1 mole of hydrogen-hydrogen bonds. We have them over here. We no longer have them over here. They have to be broken. We also have to break these chlorine bonds because they no longer exist on the other side. The bonds that we're forming 2 moles of HCl bonds. So we are going to add up the bonds that we have to break, and then we're going to subtract the bonds that we have to form. So the delta H is 1 mole of hydrogen-hydrogen bonds. Hydrogen-hydrogen is 436 kilojoules per mole. Then we have 1 mole of chlorine-chlorine bonds, which is 243 kilojoules per mole. And then we are subtracting 2 moles of HCl, which is 432 kilojoules per mole. So this ends up being 436 kilojoules plus 243 kilojoules minus 864 kilojoules, which gives an enthalpy change altogether of negative 185 kilojoules for this reaction. So this over here, minus 185 kilojoules. Ionic compounds are a bit more complex because there's not a specific covalent bond that's being broken when you break an ionic compound apart. If you have a solid ionic compound, it's a lattice, a crystal of a repeating positive and negative ions put together in like this cube structure like we looked at before. But some ionic compounds are held together more strongly than others. So in order to be able to compare ionic compounds, we have this quantity called the lattice energy. And the lattice energy is the energy needed to take 1 mole of solid ionic compound and vaporize it into gaseous ions. So that is kind of an intense thing to visualize, just these ions all flying apart into the gas phase, but that definitely would break all the ionic interactions. The lattice energy, it turns out, is dependent on the magnitude of the positive and the negative charges. So it is more difficult, or it takes more energy to break apart ions that are +2 and -2 than it does to break apart ions that are +1 and -1, which kind of makes sense. If they have a larger charge, they're more attracted to each other, it's going to be harder to break them apart. So when you do these charges though, make sure you just use the magnitude, because if you use a positive number and a negative number, the lattice energy is going to come out negative, and it's not negative, it's a positive value, the energy. You have to put in energy to vaporize an ionic compound. So make sure that you use the magnitude and not the actual negative sign for the negative charge. Also, the lattice energy is stronger for ions that are smaller. So R0 is the distance between the ions. So it's the sum of the radii of the ions. So the distance between the ions is counted as the sum of the radii of the ions. So here's from the center to the edge of this cation, and from the center to the edge of this anion. So this is the distance that we're looking at. And that is going to be a larger distance for larger ions than it is for smaller ions. So here we have a set of ions that has a smaller R0 and a set of ions that has a larger R0. And it's going to be harder to break apart the ones with the smaller R0. The smaller R0 in the denominator is going to make H lattice larger. You know, when you have a smaller number in the denominator, it makes the result larger. If you have a larger denominator, that's going to make the answer smaller. So this is going to have a higher lattice energy because they're packed together more closely, and so it's just going to be harder to pull them apart. These are kind of, you know, a little bit spread out, so it's going to be slightly easier to pull these guys apart. And this last thing here that we haven't mentioned yet is C. It's a constant. It's just a number, and it's not always the same number. It depends on the type of crystal structure. So these problems that we're going to work on, we're going to assume that the things we're comparing have similar types of crystal structure. So for example, we have magnesium iodide and magnesium fluoride, and we're saying that they have similar types of crystal structure so that we don't have to worry about what this value for C is. We're going to look at what these other things might be and see which one we think has a higher lattice energy. So pause that if you want to work on it, and also this one as well. This one we are also specifying that they are very similar as far as size goes, and also the type of crystal structure. So we're going to see if, looking at the other things that are in this formula, we can figure out which has a higher lattice energy. All right, so comparing the lattice energy of magnesium iodide to magnesium fluoride, I've put in the charges. We know magnesium has a charge of 2, iodine has 1, fluorine also has 1 as a charge. They have a very similar C, similar crystal structure. So the numerator for both of these lattice energies is going to come out the same. It's going to be equal to 2C in both cases. So the only thing that's making these two lattice energies different is the distance, the interionic distance for magnesium fluoride and for magnesium iodide. Magnesium is the same size in both of these compounds, and so we are really comparing fluorine and iodine. They're both halogens. Fluorine is several levels above iodine on the periodic table, so iodine is larger than fluorine. The iodide ion is also larger than the fluoride ion, and so this R value for magnesium iodide is going to be larger than the R value for magnesium fluoride. So here we go, we have magnesium iodide distance marked as larger, this one marked as smaller. Since this one has a smaller denominator, this answer is actually going to be larger. The smaller denominator is going to make a larger answer, and a larger denominator is going to make a smaller answer. So the higher lattice energy, the answer to this question is going to be magnesium fluoride, because that has a smaller denominator and that will give it a larger lattice energy. So let's compare lithium fluoride and magnesium oxide. This time I've just written R0 as the interionic distance. we're told that it's pretty similar for both of these compounds. So this is not going to be the big difference between the lattice energies. Also, we're told that the C's are fairly similar. So this is not going to be where the big difference comes in. This one, we have a big difference in the charges. We have a single charge lithium and fluorine versus a +2 and a -2 for magnesium and oxygen. So this lattice energy of magnesium oxide is going to be 4 C over R instead of this one, which is just C over R. So this lattice energy is going to be 4 times higher. So a higher lattice energy, and that would be magnesium oxide, and it would be significantly higher. This would be 4 times higher. So these changes in the charge have a much greater effect. This R, even though it's larger and this R is smaller, we're not going to have an R that's 4 times as long. So these effects that you see with the interionic distance tend to be a much smaller effect. The charge effect can be a much larger effect. So let's write that down here. So for the second question, magnesium oxide has a lattice energy that's 4 times larger than that of lithium fluoride, whereas here magnesium fluoride would have a slightly higher lattice energy than magnesium iodide. The lattice energies that we've been talking about cannot really be directly witnessed or measured. It's not really possible to take a solid ionic compound and instantly vaporize it to gaseous ions, and so we have to use a more circuitous route. So we can calculate approximately how much higher in energy these gaseous ions are from the compound that we started with, the solid ionic compound. And if we know how much higher this is in energy by getting there another route, and we know the position, then we can see what the position is between these two and figure out what the difference in energy between the solid ionic compound and the gaseous ions is. So it's kind of an interesting Hess's law procedure, because we take all these other reactions, add them together to get to this spot, and then we can compare what the energy levels are in order to get the lattice energy. Also, I want to point out, this is a diagram I took from your textbook. They specified that this is the negative lattice energy. So the energy comes out in this direction. That's why they're reporting this as a negative number. But your textbook considers lattice energy to be the energy needed to go in this direction, which would be a positive number. The ions are higher in energy than the ionic solid that you started with. So let's just take a look at how you could just add all these steps together and get to here. So this first step, let's say step 1, we'll call this step 1, is the heat of formation. The heat of formation is the reaction, the enthalpy of the reaction where 1 mole of a substance is made from the standard state of the elements. So we have cesium, which is a metal. The standard state is that it's a solid. Fluorine comes as a gas. We need half of a molecule of fluorine. So this would be the heat of formation reaction. So this negative 553.5 kilojoules per mole is actually the energy you would need to go from here to here. So that's going down in energy. So what we would need is the negative amount of energy for 1. So we would need to take this amount of energy and take the negative of it. Like in Hess's law, when we flip these different reactions, we want to go the opposite way. We want to go from cesium fluoride solid to the cesium solid and the half fluorine gas. So we're going to need the negative of this value, which makes it a positive energy change. We have to climb up to get to this spot. Then we need cesium to be a gas and not a solid. So this one over here, this step 2, this is the energy needed for this process. 1 mole of cesium solid going to 1 mole of cesium gas. So that's what that energy is. We have to add that in. This is the ionization energy. Remember, the ionization energy is the energy needed to pull an electron off of a compound, or off of an atom actually. So step 3 is to take this cesium gas and make it a gaseous cesium ion with a +1 charge. The bond dissociation energy is the energy needed to break 1 mole of molecules of fluorine into 2 moles of fluorine atoms, gaseous atoms. And we are doing half of this reaction. We're taking half of a fluorine molecule and making it an individual fluorine atom. So this amount is half the dissociation energy. It's reaction 4 divided by 2. So that is that amount of energy. And now we have to put an electron on the gaseous fluorine atom to make it a gaseous fluorine ion. This is step 5. This releases energy because it's very easy to add an electron to fluorine. Let's go ahead and write what half of this reaction is. So if we added all these reactions together, let's put this in a different color. So if you added reaction 1 and reaction 2 and reaction 3, half of reaction 4 and reaction 5 all together, the result you would end up with, so 1 plus 2 plus 3 plus half of 4 plus 5. If you added together all these reactions that I've written in purple, you would end up with this process here because we have cesium fluoride going to this going to this, this going to this, this going to this, and this going to this. Overall, what we've done is started here and gone to here. So we have this going to this. And if we add together the positive 553.5 plus 76.5 plus 375.7 plus 79.4 minus 328.2, we would get that positive 756.9 kilojoules per mole. That is this blue arrow over here going from this to this. So it's sort of an interesting example of Hess's law, showing how you add up all these other energies that you can look up in tables or that you can sometimes calculate or experimentally determine. And if you add them all up, you can get a quantity that you can't directly determine, but you can reason it out through this alternate pathway.